I'm going to the background. And Trifona, you are?
Are we recording?
Wait, we will wait, first of all, for a few minutes for some people to come in. Okay, we are now 19 participants. Yes. So I propose to wait for, let's say, 5 minutes, because people are joining continuously. So in the meantime, if you wish to say a few words about the SPE student chapter of the Technical University of Crete, one of you, it may be good for the people who are not familiar.
Okay, I'll start. The Technical University of Crete SPE student chapter has been established in 2018, and at this moment we are giving lectures with various lecturers and professionals in the energy industry via the Zoom platform. Now that this pandemic has all of us stuck home, and in the near future we hope we get to do lots of activities. So I think we can begin with our webinar. It's 6 o'clock. Good evening, everyone, and welcome to today's webinar titled Research and Development for Energy Transition with Dr. Olga Vizika-Kavadias. As Mr. Yodis said before, my name is Trifonas Kaitis, and I will be your host for today. We would like to thank Dr. Vizika for giving us the honor of delivering this lecture in collaboration with our student chapter. And now let's talk a few words about our speaker. Dr. Olga Vizika-Kavadias is a chemical engineer with a PhD in fluid mechanics from the University of Patras, having also spent 2 years in the chemical engineering department at Princeton University before joining IFP Energies Nouvelles as a research engineer in the reservoir engineering division. Her experience, among other things, includes a series of projects on field development processes and the modeling of multiphase and reactive flows in complex porous media, with a variety of applications such as oil and gas recovery and geological storage of carbon dioxide. Since 2013, Dr. Vizika-Kavadias has been the director of IFPEn Geosciences Division. During the lecture, you can drop your questions in the chat box below directed to me.
40 λεπτά.
Excuse me? Okay. After the main lecture, a Q&A session will be held during which Dr. Vizika will answer all the questions provided by the audience, and also during which whoever wants can open their mic or camera and ask the question in the word in person. Also, I would like to ask you to keep the chat professional at all times, and please bear in mind that this meeting is being recorded and will later be uploaded in our YouTube channel, so you can watch it whenever you want. Now, without further delay, let's proceed with our main session. Dr. Vizika, you can start. The Zoom is yours.
Thank you. Thank you very much for this introduction. It's a great pleasure for me to be with you this evening. Even if I would prefer to be with you really in Crete, but maybe next time. I would like to thank you for the invitation, to thank the SPE student chapter for the invitation, but I would like also to thank especially the friend and very good colleague, Andreas Iotis, for giving me the opportunity to present R&D for energy transition, the work we do in IFP Énergie Nouvelle. Through this talk, we will see that energy and ecology transitions are clearly underway. And we also see that R&D and innovation are necessary in order to be able to assume these transitions. I will share with you our experience at IFPEn, an applied research institute which develops low carbon, non-nuclear technologies. I will illustrate how we carry out our research, then through some selected non-exhaustive examples, we will see what are the challenges for research in energy transition and how IFPEn contributes to the emergence of this energy transition. Do you see the slides moving?
Yes, perfectly.
Okay. The global energy system is still today very much carbon dependent. The carbon dependent economy has a severe impact on the climate, leading to global warming, extreme weather patterns, and rising of the sea levels. These phenomena, in turn, are expected to have a severe impact on economic growth, as we can see these predictions presented in the BP Energy Outlook of 2020 edition, where we see that by 2020, very important decreases mostly and some increases in the gross domestic product are expected for the different area in the planet. The transformation of the global energy system to a greenhouse gas-free system will take time, we know that now, and last probably for many decades. However, what is clear today, and despite the health crisis we're going through, is that the energy transition is indeed underway. Of course, the first element was the Paris Agreement approved in December 2015, more than 5 years ago. But there are also other signs indicating that this energy transition is underway. First, more and more countries are making carbon neutral commitments. The dates, of course, differ, as we may see in this slide here, but the ambition is common. Some countries have already legislation on this subject, and this is the case for France, for example, the United Kingdom, Sweden, or Denmark. And the question is also currently being discussed in the European level for the European climate law. China is also in a dynamic of decreasing CO2 emissions. Their goal is to achieve carbon neutrality in 2060. And of course, the United States, since last November, are also engaged in decreasing CO2 emissions to achieve electricity neutrality in 2030 and then energy neutrality in 2050. Together, Europe, United States, and China count for more than half of the CO2 emissions globally. So the commitment of these three main areas on the planet is very important, is essential in reducing the global emissions. There is also another factual element, the investments. and the investments do not lie. The evolution of the investments at the global level in the various low carbon technologies, we may see them here. And we may also see here the evolution of the production of fossil energies investments, the investments in exploration and production. And 2020 was the first year where the investments in the renewables went above the investments in the exploration production area. So I think that these two graphs, side by side, illustrate the fact that we're on this switch from the fossil fuel energy to the renewable. Sorry. The World Resources Institute estimates that the total greenhouse gases were equal in 2016 to roughly 50 gigatons of CO2, equivalent CO2, with carbon emissions from energy use here being the main part, roughly 65% of all the greenhouse gases. And then the rest is distributed on agriculture, industrial processes, waste, land use, change and forestry, and the different leakings, fugitive emissions. What is important to see on this graph, in terms of the carbon emissions from energy use, nearly half of the emissions come from energy used in industry, the red part. And the remainder is roughly split evenly between the transport and the buildings. Now, if we want to economize this energy use so that we produce less greenhouse gases, what are the areas, the sectors that we can influence? Carbon emissions from activities or processes which are relatively straightforward or inexpensive to electrify can be reduced as the power sector is increasingly decarbonized. Another observation, I'm sorry, some of the slides are in French, some are in English. If you have questions, don't hesitate to ask the questions if this can help understanding. Another observation, if we look at the evolution of the global electricity mix, we see that over the past 10 years, the rate of growth of renewables has accelerated. They are now the second largest supplier of electricity. Then if we extrapolate in the years to come, and then if we anticipate a decrease of the use of carbon, of coal, the renewables can become, in the mid of the 20s, the #1 supplier of electricity in the world. And even though in 2020, we went through this COVID crisis, this does not seem to alter, to modify these trends, since the last assessment of the IEA of all the primary sources of energy, renewable energy are the only ones to have continued to grow in 2020. Always according to the IEA report, renewable energy consumption increases very rapidly for the last 10 years, and this trend will continue in the 30s and in the 40s, as it is shown in this slide, where, of course, we do some assumptions in order to do these projections? Well, you will say that all of these projections contain many uncertainties. In reality, there is not just one projection, there are different scenarios, and we see this different scenario here, again from the IEA report, 2020 IEA report. Now, what we see here is the energy consumption in 2019, and then the projection to 2030 for 4 different scenarios. We were looking a little bit closer to these 4 different scenarios of IEA. The STEPS scenario is the stated policy scenario, the scenario incorporating the current commitments of different states in the Paris Agreement and estimating that the COVID crisis will end in 2021. The DRS scenario is the delayed recovery scenario, same assumption as the previous one, but an exit from the crisis in 2023. The SDS, the Sustainable Development Scenario, is the scenario respecting the limit of 1.5 degrees centigrade of average temperature increase in the globe with carbon neutrality in 2070. And finally, this new scenario that appears for the first time in the IEA report this year is the scenario where we'll have net zero emissions by 2050, but which is also much more ambitious and more difficult to follow, more difficult to attain. So according to IEA, there is a need to activate a whole set of technologies as illustrated in this slide in order to be able to decrease our greenhouse gas emissions and in order to be able to respect, to follow one of the more ambitious scenarios. For example, in 2030, respecting the Paris Agreement, hypothesis of the SDS scenario, stated policy scenario, would lead to a reduction of around 10 gigatons here of CO2 emissions per year, but by using different low carbon technologies, some of which are not mature, as shown is the graph in the right. In fact, in 2030, only one part of 26% of these technologies will be mature. If we want to engage the carbon neutrality, we must aim the SDS scenario, which is a real challenge. And for this, we should be able to deploy low carbon technologies in different sectors, as it is seen in this graph here. Electrification, the blue part, hydrogen use, but also CCUS for a main part also, which means carbon capture, use, and also storage. Achieving the objective of carbon neutrality requires sustained efforts in research and innovation. It will require breakthroughs to increase the performance, to reduce the cost, to accelerate the development of the different processes. Of course, you will say these are projections, but I think that this give a very interesting light in what we have to be prepared for and in the efforts that we have to do in our everyday life, but also in terms of industry development, development of technologies, and so research and innovation. Another interesting element of the transition is the decarbonization of the mobility. The momentum is launched on electric vehicles. 9 million new electric vehicles were sold worldwide in 2020, and this is 50% more than the year before. It is therefore a main solution that is clearly gaining momentum. However, we have to admit that this very small part here remains really marginal. And even if we do these projections, rather optimistic projections to the fleet at 2040, we see that the electrified part of the mobility is only a very small part, attaining roughly 25% of the whole mobility. So that means that we need other solutions. This is okay, this is very good, but this is not enough. We need to prepare also other solutions, and these other solutions would be to reduce the environmental footprint of the sector by optimizing, for example, the mobility management, or by using other type of fuels like the biofuels, and especially second generation biofuels may have an important impact in this equation. Just look in the funding of this research. If we look at global public R&D funding, global public R&D expenses in the energy sector, we will see that they are overall stable in the last decade. So here we see this funding from the 70s, 1970, up to 2019, roughly stable in the last decade with this distribution that we see here, and of course, a decrease of the fossil fuel funding, increase of the renewable funding, of the cross-cutting research, and on the energy efficiency. However, this seems not sufficient because the target that we have to achieve, it is very ambitious, it is very important, and public R&D does not seem able to follow this ambition, does not seem able to fund in an essential way this very important transition. So I guess the message here is it is important to have the public funding, but we must mobilize also the private actors. Direct private funding towards low carbon technologies will be absolutely necessary in order to be able to meet the objectives. So how can research and innovation help accelerate the energy transition? I will start with 2 words about IFPEn, and then I will show you how we develop our research and innovation to serve the low carbon energy, to serve the energy transition. We are a public sector research and innovation body. We are also a training center through the IFP school and through also an important number of PhD students working in our laboratories. We also are part of an industrial group through our subsidiaries. Roughly 1,700 people, roughly 1,200 technical people, engineers and technicians, and roughly also 300 million euros of annual budget that has been reduced in 2020 due to the COVID crisis. As you may see, the sum of the budget allocation by the government and our own resources in 2020 was a little bit less than the 300 million of euros. Our mission and our challenges also is in the context of the climate change and the ecological transition to foster sustainable mobility, to diversify the energy mix, to increase the energy efficiency, and to improve the environmental impact of, decrease the environmental impact of the fossil resources. We have three priority areas: research and innovation, but also training, as I said, and value creation through our subsidiaries, and also the creation of new subsidiaries or other structures of valorization of our research. Around 10,000 active patents, 175 basic patents filed in 2020, more than 200 publications, scientific publications per year, and roughly 130 to 150 doctoral students and postdoctoral researchers in our laboratories. So this brings me to the presentation in a few words of the specificity in this area of our research. In other words, of our strategic priorities, which are for climate, environment, and circular economy, renewable energies, and sustainable mobility. And these three are in the part of the energy transition area, and of course, our historic activities, responsible oil and gas. Now, if we look closer to each one of these priorities, climate, environment, and circular economy is a new one, and is about reducing the impact of human and industrial activities on the climate and the environment. Renewable energies is about developing solutions to produce energy, fuels, and chemical intermediates for the renewable sources. Sustainable mobility is about developing effective, environmentally friendly solutions for the transport sector. And finally, responsible oil and gas. We still work on the oil and gas technologies, but to propose new ones that meet the demand for energy and chemical products and reduce the environmental impact. Our research is based on our fundamental research, which is the bedrock supporting the development of our innovations and represents 30% of our budget. Now, I will illustrate with some examples each one of these four strategic priorities. So follow the colors in the slides to come. First, climate, environment, and circular economy. We work on developing chemical processes for recycling plastics. We work on capturing, storing, and using CO2, analyzing the air quality, carrying out environmental monitoring, and developing life cycle analysis as a part of the circular economy studies. Three examples from this area. The first one, a project, a European project on a process demonstrator on the construction of a demonstrator for steelmaking gases, capturing CO2 from steelmaking gases with ArcelorMittal plant. A project that started in 2019 and goes on for another 2 years. A second case, real e-connected suitcase to analyze the gas composition for straightforward and fast evaluation of the vehicle emissions in real use. And finally, a project on the chemical recycling of plastics. And then I will focus a little bit on the chemical recycling of plastics because it is very important from oil points of view, products, and also energy. So this slide is in French. I hope you can follow. Recycling of sorted plastic waste with mechanical waste makes it possible to recycle a part of the volume of plastic. But by adding chemical recycling, the recycling potential is increased by an order of 10. What we can do with chemical recycling, we can deformulate the polymers and then reformulate. We can depolymerize, so we can go back to the monomers and then repolymerize to produce new polymers. And also we can go up to the conversion to the molecules and to do new synthesis and to produce new chemical products. So this is an area which is very important, very hot, that needs to master chemistry issues from a practical point of view, but also from a theoretical point of view. An example here is part of our work devoted to the recycling of opaque polyethylene tetraphthalate. So removing the color pigments is very difficult, but it is essential, and we've been working on this subject for many years. Now we're at the stage of starting a demonstration project with a Japanese partner who has the experience in recycling of textiles. And that was the good point to start. That was the very important advantage of working with an industrial partner having this technology, recycling textiles, having the first matter for our technologies. So the complementarity is very important, combining our forces to change the scale in terms of the deployment. And our goal is to have a demonstration finalized in 2023, that is to say tomorrow. And this is to compare, of course, with 10 years back required to deploy the process. Now we go to the renewable energies. In the area of the renewable energies, we work on the production of biofuels, on developing processes for bio-based chemistry, so byproducts, developing offshore wind power, marine energy, and massive energy storage, managing the underground environment safety, and also producing and storing hydrogen, which is a relatively new activity. So 3 examples, developing technologies for the ecological transitions: the offshore wind power with the innovation on the technology selected in the framework of a public funded project in France for floating wind power. But I would like to focus here in the production of second generation biofuels. 2 projects, one process for the production of lignocellulosic ethanol, and another project with the thermochemical conversion to biodiesel and biokerosene. Just a reminder that we have 2 types. Excuse me. We have 2. We have 2 types of.
Maybe we can take a short break for a glass of water.
Okay, so I was saying there are 2 types of biofuels. The first generation biofuels, which transforms part of the food biomass and is very strongly supervised today because of this competition with food. And the second generation here, which is the transformation of agriculture and wood residues without competition with food. And it is essentially on this path that we have been actively working for more than 10 years now, involving either a thermochemical pathway using a thermochemical pathway or a biochemical pathway using enzymes to transform wood into ethanol. Today, these 2 paths are mature, and the R&D has demonstrating the feasibility to industrial scale. So the process at commercial stage is the project Futurol. The 2 second generation biofuels are very important to decarbonization of the mobility because they have a significant reduction in greenhouse gases. As we see here in the life cycle analysis studies, the second generation biofuels are expected to allow us to gain up to 70 to 80% greenhouse gases emission compared to a conventional fluid, as is the case, for example, for the bottom of the slide here. And it is even more interesting that the electrical vehicle, as you may see also in the same slide. So second generation biofuels are very interesting for energy transition from all points of view. Of course, these processes, these different technologies, are also very important for the production of bioproducts. And these are some examples of this production of bioproducts. First, to produce bio-based butadiene, the key element in the manufacturing of tires. Second, the development of a technology for the production of bio-based ethylene by dehydration of ethanol produced from fermentation. And the last one, the process to produce basic bricks, such as benzene, toluene, and paraxylene, for production of plastic and textile fibers. Before moving to the sustainable mobility priority, I wanted to cite a key theme for the energy transition, which is the energy storage. I won't have the time and not the right example to develop here, but I wanted to stress the importance of the work on the batteries. The purpose is to continuing to increase the efficiency of the batteries, the energy density, and to reduce the cost. And in this field, fundamental research is needed, work in electrochemistry, chemistry and physics of the materials, solids and fluids. This is really fundamental. More research is needed in this area, and of course, more demonstrators and development. Now to the sustainable mobility area, we develop vehicle electrification, offering solutions for connected mobility, improve internal combustion powertrains, and optimize the use of alternative fuels, like the biofuels, for example. 3 examples: the electric motors, range of highly efficient, low-cost, synchronous reluctance electric motors. Connected mobility, with an application for mass smartphones evaluating pollutant and CO2 emissions related to individual mobility. And hydrogen engines, developing hydrogen engine solutions, internal combustion, and fuel cell also. And the illustration is more on this last one. The test, real test of an internal combustion engine of hydrogen, a test that has been run a couple of months ago. And you see here the simulation of this type of engine. And the purpose is, and the target is, to be able to optimize the combustion through the simulation and optimize also the design of the engine. In the last area, of course, responsible oil and gas is also one of our main priorities. We work on producing clean fuels. We work on converting and purifying heavy crudes and residues, producing petrochemical intermediates, processing and converting natural gas, refining, understanding and modeling the underground environments. This is more the upstream, increasing the production of with enhanced oil recovery, and also producing offshore. So we cover with our different technologies the conventional upstream of the petroleum industry and also the downstream with different applications and important projects from the lab to the field to the pilot, and all of them more than 100% funded. Something that is also very important, and is a point that I would like to underline, is the way we organize and we coordinate our fundamental research. This approach is structured around 9 main challenges, 9 main objectives, which mark out our scientific approach. It goes from the understanding of the physical phenomena, the understanding of the physical and chemical phenomena, through the modeling to the evaluation of the complete system. So these challenges are transverse and in most of the cases interconnected. It is about the characterization of different material, fluid and solids, about the reaction mechanisms, the effect of the containment on the flows, the use of massive data, the identification of descriptors of the physical phenomena in study, the modeling of multi-coupled phenomena, the use of development of command and optimization techniques. We work on code performance. And finally, another transverse challenge concerns economic and environmental assessment involving mathematics and social sciences, integrating societal acceptability issues, which provides decision-making support methods and decision-making tools. By breaking down the application problems into scientific questions, this approach allows us to orient correctly our fundamental research, to optimize our efforts, and to bring key groups together, working at the interfaces of the different disciplines, which is absolutely necessary if we want to go further, if we want to achieve our targets. So we'll illustrate with a couple of examples our fundamental research, starting with numerical techniques for chemistry. Historically, numerical modeling has brought a lot to chemistry. One can cite, for example, molecular dynamics, permitting to represent molecules and their interactions. I chose here an example of quantum computation that the computing power of recent years has permitted, has made possible, as well as the improvement of the codes. We're more relevant now to simulate more complete systems associating the molecule and its environment, and to predict, for example, the reaction rates with ab initio simulations. We have in this image a system of 500 simulated atoms in a reaction aiming to produce bio-based chemical intermediates. The results of these calculations will allow us to better manage and control our processes. The numerical simulation of 4D phenomena, including space and time, such as the combustion or the storage of CO2, involves a large number of chemistry calculations, that is to say, at any discrete point in space and time, and we know how much expensive is that. Each chemical calculation involves a full simulation operated by a complex model involving a large number of interacting chemical species. So it is very important to optimize this calculation. Optimizing the calculation time of this model is really a performance issue. Deep learning methods can be used to take advantage of the volume of data generated by all these chemistry calculations in order to build a predictive model that is both precise and efficient, so that we avoid to run the detailed calculations every time we need to solve the problem. Finally, what we also develop and use is what we call the QSPR methods, quantitative structure property relationship. It is about to start with target property, the property that we want achieved, the property, for example, that we want for our catalyst to have, for example, and deduce through the modeling and the calculation the shape of the molecule, the structure of the molecule that will give us this property. So the idea is to use computer resources to solve chemistry problems, working on chemistry databases, existing databases, or the databases that we will build, we will create through our very detailed numerical calculations. And so we can extract information, we can extract new models from this knowledge. What is very characteristic in what we do is this need to have different scales communicating. It is very important in the case of catalysts, for example, to be able to understand what happens in the microscale, to be able to understand what happens in the mesoscale, and then in the macroscale to the pilot. So we develop experimental tools that permit us to observe, to measure, but also numerical tools, models that permit to test our assumptions and permit also to improve our models based on the experimental observations. And this communication between the different scales, from the microscale to the pilot scale, it is not one way, it goes both ways. We have to go down the scales to understand in the macroscale, and then up to compare, and then down to correct. So it is an iterative method. It is very important for the success of our models and of our research. Now, this multi-scale approach is also very common in the geosciences. This multi-scale approach is something also very developed, given the different scales in the geosciences context, where we have to go from nanopores to the basin scale, and from the nanoseconds, the characteristic time for a reaction, to the millions of years, which is the characteristic time of the creation of the reservoir or a basin. And so again, this approach, multi-scale approach with the coupled phenomena, is something that is basic to in our research for the conventional hydrocarbon studies, but also for what we have to develop for the future in terms of tools and skills to help the energy transition. So some words about the energy transition and what the geosciences can bring to this energy transition. Given my past activities, I could not finish this presentation without saying some words about that and without bringing some examples. The reason I insist is that at least at IFP, historic geosciences skills, tools, and methods have been developed for the hydrocarbon-related subjects, and these methods can perfectly fit to the study of low-carbon energies and climate change impact. Geometry modeling, fluid flow simulation, and laboratory and field measurements, as they have been used in the hydrocarbon area, can now be transformed, adapted to serve new areas and to bring new answers to new problems. Geothermal energy, geomorphology, hydrogen, CO2, and soil carbon stocks. I won't talk about hydrogen. It's too new, too recent. And I will not talk about CO2 because it's too known. We presented several times. I prefer to illustrate three other examples, three new examples: geothermal energy, the geomorphology studies, and the soil carbon stocks. The skills acquired by IFPEn in the field of hydrocarbons are naturally adapted to the geothermal energy theme. However, knowledge and tools related to model allow to explore the potential of certain areas, to assess the risks associated with the presence of these areas of hydrocarbons, of CO2, or even of H2S. We can use our expertise and our tools in natural refractory reservoirs, because in most of the cases, geothermal reservoir cases, the reservoir is fractured. Understanding the fracture reservoirs is very important to be able to correctly predict and to be able to size also the installations. The risk of corrosion and scaling, new subjects that can be treated with the same skills as for the hydrocarbon questions. The deep or ultra deep also reservoirs are very important. Being able to identify these reservoirs, being able to evaluate their potential, and being able also to correctly analyze the risk is very important for the development, and can be done with the skills, the tools, and the methods that have been developed in the hydrocarbon areas. Something that is really new is the use of the stratigraphic modeling to study the surface geomorphology. As you may know, the stratigraphic modeling tool is a tool that allows to account for the processes of erosion and the filling of basins throughout the geological ages. And these tools can be used now to develop towards the modeling of processes that affect the landscapes. Among the different points that can be examined, the watershed evolution, the base sand filling, the soil erosion, or even the water resources, availability, and the fate of the water resources. And in the picture here is the Mont Saint-Michel, which is inscribed in the UNESCO World Heritage List. And this is one of the sites that we are studying with this stratigraphic modeling tool. Finally, and this is my last example, the soil carbon quantification that can be done with the methodology and equipment that has been developed over the years to characterize the organic matter from sedimentary rocks and to quantify the possibility of having hydrocarbon reservoirs in these sedimentary rocks. Now, this tool can be used to quantify the organic matter in the soils. And this is something which is very important because the study of carbon in soils, the soil can play an important role in carbon sequestration. And then using this tool, we can analyze the content of carbon. We can analyze the potential of the soil to store CO2. So we can evaluate the potential of the 4 per thousand initiative that has been launched by COP21. That is to say, we can assess the impact of agricultural practices on carbon stocks in the soil and therefore on the concentration of CO2 in the atmosphere, because these two communicate very closely. So in conclusion, what are the challenges for research and development? We have a target which is very ambitious. And the goal of carbon neutrality has to be achieved. We have also a dynamic that is set in motion in different places in our planet, in different levels, political, social, and scientific too. What we need to mobilize research, and mainly research at interfaces between discipline, cross-cutting research. We have also to mobilize funding providers, public or industry partners. We need to do substantial research and innovation effort on low carbon technologies to increase the efficiency, to reduce the cost, but also to go further by completing the industrial deployment of technologies existing already, but needing validation and deployment. And I would say, as a last word, what we need to do with that, we need to be able to combine research, innovation, development, and training, and being able to iterate between 3-4 main forces to achieve our goals. Thank you for your attention.
Thank you very much, Olga. This was a very insightful presentation. Let's proceed to the Q&A session. Trifona.
Thank you, Dr. Vizika, for this presentation. It was really interesting. And now let's proceed to the questions. The first one comes from Birlis Emanuel. He's studying petroleum and natural gas technology engineering at the University of Kavala. And he asks, is there any way to increase or maintain energy at high points?
I'm not sure I heard the question.
Yes, he asks, is there any way to increase or maintain energy at high points?
High points.
Yeah. Maybe if he likes, he can open his mic or camera and provide further.
Maybe a clarification of the question.
Okay. Maybe we can proceed to the next question.
Yes. He says his mic doesn't work. So.
Okay.
The next three come from Harilos Mariolakis. He's an officer, he's the vice president of our chapter. And the first one says, on the way of reducing carbon emissions, could synthetic fuels be an important asset?
Synthetic fluids other than the biofuels, synthetic fluids, you mean For example, hydrogen.
I think.
As I showed in the slides, the biofuels have the best total.
For example, Porsche is implementing a new technology for developing synthetic fuels by chemical procedures, if I can remember correctly.
Chemical procedures. What I was saying about the biofuels, for example, the biofuels like ethanol that you can extract from wood, for example. This is a synthetic fluid, and this is something that has a very good balance of CO2 according to the analysis that I've shown, the data of International Energy Agency, much better even than the electrification of the vehicles. And this is something that can be easily used also in engines for in aviation, which is not exactly the case for hydrogen, for example. Yes, in this sense, the synthetic fluids are a very good alternative, are probably today the best alternative to the hydrocarbon fluids.
Okay, next question is, do you believe a large-scale implementation of hydrogen usage as an internal combustion engines fuel could be achieved?
I think that using hydrogen is really a very, very big challenge. Technologically, it is possible. We still have to work on the efficiency. We still have to work on the optimization. The main problem, I think, with hydrogen, which is a very good fuel, the main problem, I think, is the security issues. This is the reason I was saying you're not going to use hydrogen in the airplanes, for example, in the aviation. I would not believe to the use of hydrogen for personal vehicles. I would expect these technologies to develop rather to the professional fleets or the marine, for example, transport. So maybe you're not satisfied with this answer. I think that there is not only one technology that will save the climate and that will give answer to all our questions. I think that the answer is a combination of different technologies, the combination of different possibilities, each one adapted to a different context.
Okay, and the last question from Harilaos is a really long one. He says, what would be a more real and easily achieved scenario? Keeping current vehicles and investing in more eco-friendly fuels and technologies, or a total transition to EVs? How about the excessive installation cost of renewable energy sources, as well as the transition cost?
Yes, As I was saying, there is not only one answer to our problem. IEA's study shows that we have to combine different technologies, and from now to 2050, and then you have to work towards making these different processes more reliable. What is very important also is for these different solutions to run what we call the life cycle analysis. This means taking into account in a global way the performance, the efficiency of a proposed solution. And this is very important because we use energy to produce products, to produce fuels. So by using energy, different types of energy, we produce more or less greenhouse gases. I'll give you an example. Hydrogen, for example, all hydrogen are not good. There is the green hydrogen, which is obtained through electrolysis. There is the gray hydrogen, which is the way we produce hydrogen now, actually, through fossil fuels. And there is also the blue hydrogen, I simplify a little bit, which is the hydrogen which is produced using fossil fuels, but with capture of CO2. So you see, all hydrogens are not the same, and all three hydrogens do not contribute the same in the economy of energy and in achieving our target. So different solutions, different technologies have to be tested with life cycle analysis in order to be able to see in a global way the impact in terms of pollution, in terms of emission, in terms of efficiency of the use of energy.
Okay, thank you. And the next question comes again from Birlis Emanuel. And now he asks, do you believe that in depth of time, natural gas will replace entirely the non-friendly hydrocarbons like petrol?
I believe, I see that natural gas has a global contribution, more favorable, let's say, global contribution to greenhouse gases than the petrol. I think that there are applications where the natural gas can replace oil in a very advantageous way. I think also that there are lots of things that we cannot do with gas, especially one part of the chemistry, one part of the production of chemical products. So natural gas is already taking part from oil. What we see is natural gas progresses a lot, and the projections show that the gas will keep progressing, and the oil will decrease more and more. However, I think that there are main applications, especially all the petrochemistry, that cannot be done for the time being without the oil.
Okay, and the next one comes from me. It's a little bit general question. And do you think that nuclear energy could be part of the energy transition? I mean, a more controlled nuclear energy, could it be the future?
Well, the answer is almost political. Some countries have invested a lot on nuclear energy. France is one of these countries. 80% of the electricity in France comes from nuclear energy. This is very important. This is a unique example. And this confers a certain independence, autonomy. However, there are many shortcomings in these approaches. What we see, and you may have noticed in the presentation, in the IEA projections, and also in the observations, what happened in the last 20 years, for example, nuclear remains almost stable. So I would not say that this is an energy to generalize. This is not the way we go to today. But for those who have done the investment, and these are very important investments, it is a very important solution also. France was one of the first countries to respect the commitments about greenhouse gases emission. So everything is not black or white. It is more difficult than that. The options for the future are really very, very complicated.
Thank you for your answer. And I think we have no more questions. Whoever wants can drop them now.
Can I make questions? Yes, please go ahead.
Okay, Dr. Gildas.
Go ahead, Mario.
Hi, everyone, and thank you, Dr. Vizika, for this beautiful presentation. Actually, I've also looked a lot of things from IFP through the years, because IFP does a great job through the years about energy transition, different kind of MOOCs and stuff. And you saw a lot of difficult things, I would say, that no one asked until now. So I will go through the boring stuff, I guess. You throw a lot about simulations and deep learning and about CFD as a chemical engineer. So we can talk a bit about that, I guess. What kind of softwares do you use? Do you use any commercial like Fluent, or you have your own in-house code? And how do you tackle the problems? Like, do you go through the implicit way or the explicit method? And I don't know, this slide that you saw about going to the micro scale and then again to the reality and up and down, how does this work? I mean,
Good question, very technical though. Okay, we use Fluent, everybody uses Fluent. But we also develop our own simulations at different scales. So we, for example, for the post-media flow, we develop lattice Boltzmann models. We develop Pore network models, and we couple the lattice Boltzmann to the Pore network because this permits to go to the scale above. We develop, of course, our own reservoir simulator that can be also used in the core plug scale with average parameters, average properties, the usual average properties. We deploy the reservoir simulators in the big scale. We have specific cellular automata simulators for the geological process, different geological processes, for example. And we have also in the very big scale basic modeling. So we use commercial simulators, but we also develop our own simulators, or in the commercial simulators, we develop our own cars. For example, we use the Convert simulator to model the inner combustion engines. And in this simulator, we're able to develop our own parts for our own studies. Is that part of the answer that you expected?
Yeah, indeed it is. Yeah, I think from many of your slides, we could talk for hours about these things. Like even one slide can be like 1 hour of conversation easily.
Yeah, even more than that, if you have if you have the experts. Yes. My expertise is more in the geosciences, petrophysics area. But for example, I can tell you that the molecular dynamics simulations for the different chemical species and the kinetics of the reaction, we develop our own simulators in collaboration sometimes with academic partners, but we develop our own products.
Okay, nice. When you say kinetics, you also go down to microkinetics for the reactions.
Yeah. This is what this is the slide I showed on the quantum simulations, and then the study of the kinetics of the reactions, and then different runs, and the study with deep learning methods or QSPR methods in order to extract macroscopic models.
Okay, thank you for your answer. And May, if I can have one more question. Trifon, I hope it's okay with time. And congratulations, you're doing a great job, actually. I wanted to ask you your opinion because you mentioned hydrogen, but because it's a kind of new, although it's also old, but now it's again in the news, I guess. You don't seem, in my opinion, you don't seem to have a really faith on it. So what do you believe about hydrogen? Many people are researching now, like in terms of the future, when do you see that can be applied commercially?
I think that it's very important to keep working on the project. I think that it's very important to take into account this the different ways we can produce hydrogen, because we will produce hydrogen actually. Okay, we produce hydrogen every day for different applications. But as I said, this hydrogen is the gray hydrogen. It comes from fossil fuels. It's not good for our climate, and in terms of CO2 emissions, it's very bad. So what we have to do is either work on electrolysis, so hydrogen from water, but this hydrogen is very expensive. So we have to work on how to make these technologies less expensive, adapt pressures, temperatures, materials, electrodes, make it less expensive. It's 10 times more expensive than the hydrogen coming from the fossil fuels. Or work on the technologies that from the production of hydrogen from fossil fuels, they capture the CO2 and then they store the CO2 or they use it in a correct way. So this also needs still work, research, fundamental research, applied research, and also deployment, pilots. to see that. So yes, I believe hydrogen. I believe that as a solution is one part of the solution. As IEA indicates, hydrogen is an important part of the solution. The solution, the global solution of avoiding CO2 in 2050 consists of different contributions. Spending less, the best CO2 is the CO2 that we have not emitted. Storing CO2, using hydrogen, but using hydrogen that does not produce CO2 to produce it. Better performance, efficiency of our engines, biofuels, and so on. So in this mix, I think that the hydrogen will play an important role. Said simply that there is still work to do, and that for security reasons, for security purposes, I would not see hydrogen in the fleets, in the personal vehicles. It is extremely risky. Hydrogen is not an easy fuel. The big success of the conventional fuels is that not only they are not very expensive to produce after all, but also that can be stored easily, they can be transported easily, and they can be used without main risk. And in these three questions, hydrogen does not really fit. It is difficult to store, it is difficult to transport in the same way, and it is still difficult to use it in our personal vehicles. I would do that. So yeah, I think that it will be limited to either industrial applications or to the transport, professional transport.
Thank you.
This is just my opinion, okay? And this does not engage IFPEn either.
No, I think it's not just an opinion. I mean, I guess we have some doctors here, like Dr. Yotis, Dr. Marinakis, and maybe others, Dr. Bellas, I see. So people who know about hydrogen, and as you mentioned about the dirty way that we basically produce it and the transportation and all the challenges with hydrogen. But I guess many students who are the most participants right now, they don't know. So it's good to make some clarifications about that. And also that doesn't make it an opinion. It's like a fact. And if I may to close with that, because I believe Trifonos doesn't have more questions. I don't know you, Dr. Yotis.
I have a question, but please go ahead.
Okay. So what would you advise from all your experience working all these years, both in petroleum and the reservoir, and also to the energy transition, to renewables, new young engineers that want to take a bachelor thesis, a master thesis, to pursue maybe a master or a PhD, or which kind of field should they go?
Well,
in this, of course, energy transition scheme, I mean, like geothermal, you mentioned in the last slide, CCUS, and yeah, things like that.
I think that the energy sector is really crucial. I think I think that being in the energy sector for an engineer, it is very important. The challenges are very important, and the solutions to be found might be thrilling. So I would recommend, depending also on the skills, on the background, to go to the energy sector. What is also very important, as we know and as we've seen, is the chemical industry. most of us are chemical engineers. I think that the chemical industry is something that is about to be revolutionized with these new challenges and the new objectives to respect the commitments about CO2 greenhouse gas emission. So there will be many challenges depending on the background. I think that this, what is very important is to, well, this is trivial, is this really like what you will choose to do. There is a very important development, and there are different studies and different projects on what we call the communication between the engineering sciences and the social sciences. And this is not just communication. This is not just how to communicate to the public. This is really a dialogue that has to be installed between the society and also the scientists, the engineers. What we've seen through the COVID crisis is that the scientists are not really, how to say, the credit of the scientist is not really on the top. At least this is what we observed in France. I don't know if in Greece things were different, but in France, I would say that was really alarming to see that the scientists do not really have a very big credit in the population, in the society. So I think that everything that all the skills and all the talents that will bring closer the science, the engineering, and the society, because all we do is for the society. This will have also a very big future in the years to come. Well, this is my answer.
Thank you so much for all your answers. I hope I didn't tire you so much. I would like to thank you once again for accepting our invitation and for your very interesting presentation, as well, of course, Professor Yotis for making all this happen under some technical difficulties that we had here at Technical University of Crete these days. And I think that's all from me. I think, Professor Yotis, you have some questions.
Yes, so thank you, Maria. I really enjoyed the question of Tryphonas. It was a daring question regarding nuclear energy. And I also enjoyed the answer.
I hope so.
I also enjoyed the answer. It is not well known to everyone that 80% of the electricity in France comes from nuclear power. And so this a little bit demonization of nuclear power, this has happened before the current demonization of oil. So it's like history repeating. Anyway, another part of that I sensed in Tryphonas' question was the central production of this particular energy source. So centralization of energy production seems to play a very important role to the future of this so-called energy transition. So in my opinion, and I also would like your opinion as well, we are talking about a diversity in the years to come, the next 20 or 30 years, a diversity of different energy sources Okay, so we will not depend on fossil fuels by 80% globally. And by fossil fuels, obviously, we are also including coal, oil, methane, but we will equally depend, and I think this may be part of the solution, we will equally depend on several different forms of energy and energy sources. So another second pillar of this energy transition is centralized production of most of the energy. Okay, because if we have, for instance, cars running on petrol, we have several sources of CO2 producing a global CO2 footprint that we cannot control so easily. And then a third pillar is, in my opinion, would be to raise public awareness in order to reduce energy consumption per capita. So the technology is here, but some countries, especially for instance the United States, decide to be, or their way of living is more energy intensive. So I guess these three pillars, diversification, centralization, and let's say energy usage awareness, are three main pillars towards energy transition, besides the technological developments. I would like to know your opinion on this long statement from my part.
Okay, so diversification, very important. I didn't talk about that, but renewables are more suited to diversification issues, diversification problems. You may, in France, for example, there are different projects to develop different technologies in different regions. All the regions are not the same. In France, there are very cold regions on the north. There are very hot regions in the south. It wouldn't be reasonable to install, for example, photovoltaics in Lille, for example, or even I don't know, even more in the north. It wouldn't be reasonable to install wind engines close to Paris. Okay, so the renewables are more adapted to this diversification and also the independent development of energy solution for the different regions. This is very important. Now, the public awareness. Yes, I said already, the best CO2 is the CO2 that you have not produced. That means the CO2 that means the energy that you have not used, you have not spent. This needs, I agree, public awareness, and this is not simple. So this is why I was saying the communication between engineers, scientists, and the society is something really very important, and it's very important from a research point of view, and not only the social sciences as we used to know before. It's something that is has different dimensions, from the theoretical point of view to the practical point of view to the communication issues, of course. What is also very important is that we have sometimes the wrong good solutions. I explain myself. We said, for example, that due to the COVID crisis, we traveled much less, so CO2 emissions from the transport was really were decreasing in 2020. Something that has been observed also is that the CO2 emissions due to the use of different communication tools started to be important, and so they have to be taken into account in the global balance. The capacity we have today to use data make us really eager to have access to the data, to have the tools to use this data. And as the computers are more performant and they produce more data, we need this more data. So there are serious studies, and I don't want to give you the numbers because I'm not sure, but it is really important. All the use of different data, massive data, because the technologies are today accessible, are very energy consuming, and so they are very CO2 producing. This is why I was saying globally. We have to see the things globally. Okay, we stay at home and we don't travel, and then we produce less CO2. But what if, for example, through the telecommunications, we produce as much CO2 as before? Okay. We have to see the things globally. I think that the education is something very important. This is why my last sentence was, we have to do research, we have to do innovation, but we have also to do the training from any point of view. Education, high-level education is really very important. Otherwise, we were more vulnerable to the wrong good solutions. Okay. So yes, I agree with what you said.
Okay, I'm very happy about this. Okay, so thank you very much. I have no more questions. I think it was very tiring for you. So, Trifona or Maria?
Okay, is there anything else you want to add, Dr. Vizika? Any last words?
That's very frightening, Trifona, for our speaker. Any last words?
It's up to me.
I think it's okay. There are no last
okay,
words.
So thank you all for attending today's webinar, and especially all those of you that have stayed until this moment. Thank you again, Dr. Vizika, for delivering such an interesting webinar. And of course, Professor Yotis, our faculty advisor, for his valuable help.
Thank you very much.
You will find all our, okay.
I really appreciate it. I regret the fact that I cannot see you. This is very unpleasant to talk to a screen. I hope that next time I'll have the opportunity to be there with you.
I really hope so, that we can arrange a similar seminar live in person in Crete when all this is over.
Yeah, a pleasure.
And does anyone want to open their cameras? Because Marios, our president, asked that.
Right.
And I don't know what he's up to.
I think it's no, it's nothing. I think it's nice to open the cameras. I was thinking it from before. Yeah, I understand it's not nice to speak to nothing, right?
Mm.
And Harry, if you can take also a nice screenshot with everyone who is until this point. I mean, yeah.
So are we finished?
Yeah, I think we are good.
Okay. Thank you very much, Olga.
Thank
Okay,
you, everyone.
you.
Bye, everyone.
Bye.
Have a nice
Bye.
evening.
Thank you very much. Have a nice evening.
Bye bye.